Right. Good morning, students. Okay. So, in the last class, we are discussing about the Bohr's theory, right? We started about the Bohr's theory. Okay. So, we'll continue today, right? So, what we discussed in the last class, Bohr's postulates, four postulates we discussed. What are those four? Trying to recall those. First postulate is nothing but the same that taken by the Rutherford's model. Electron is revolving around the nucleus in the circular orbits, right? Second postulate is very important. What is that? Angular momentum. About angular momentum, he discussed. What is the angular momentum, which is equals to nh by 2 pi. So about that story and all, I think we have seen in the last class. Next, third postulate, very important. What is that? So what is Rutherford failure? If an electron is revolving, it is accelerating, he said. But according to Bohr, what he said, electron which is revolving around the nucleus will revolve with a constant speed, and the acceleration is there. But what type of acceleration? Radial acceleration is there. Due to radial acceleration, what will happen? It is used to change the direction of the electron. It won't give any speed to the electron. Right? So he said it's like the uniform circular motion. Electron will revolve around the nucleus with a constant speed. While revolving with a constant speed, there won't be, third point, there won't be any energy which is radiated. Okay? So in spite of the energy which is there towards the center, but still there is no energy which is radiated because electron is revolving with a constant speed. Tangential force is zero. Tangential acceleration is zero. Right? Next, what is the fourth point? Electron can radiate energy, but when it is trying to jump from lower energy level to higher energy level, it has to take some energy. So it is coming from higher to lower, it has to release some energy. It can radiate some energy outside in the form of photons or gamma photons. We'll see later in the nucleus. What particle will come out, we'll see later. Okay, so this is the thing. So it can radiate energy when moving from one orbit to another orbit. But in the same orbit, it won't radiate any energy. That is the conclusion in the last class, right? So now we'll continue the discussion, right? So Bohr theory of hydrogen atom. Bohr's theory is applicable according to him. In disadvantages, we will see what is the disadvantages and all. In today's class or in tomorrow's class, we will see about that. But according to him, his theory will be applicable for all the types of atoms. But he did his experiments based on the hydrogen atom. Why? Because it is very easy. Why? Only one electron will be there in the outermost orbit. He can do some experiments only on that one electron, whether it is going to the higher energy levels or not. So what is the radius of the orbits or not? We can calculate it easily. Why? Because only one electron will be there in the outermost orbit. So that's why he did his experiments on the hydrogen atom. But we can do it on the atoms, but he can say the hydrogen atom, and he did all the experiments and all the things what he want to do on this hydrogen atom. Right? So now what he did, same thing. So first point, so he considered the nucleus. He considered nucleus and here. So electron is revolving around the nucleus. So assume here electron is there, which is revolving around the nucleus. First essence, that is nucleus, right? So the charge of the nucleus, I can write it as Z, and assume the electron is revolving. Electron is revolving. Z times of E, and electron is revolving. So tangent will give you the direction of the speed at that instant, right? So the tangent will give you the direction of the speed at that instant, right? All these things we know, we already studied. Now, what is the basic thing he took from Rutherford? Or whatever the Rutherford derivation we did, we calculated, I think, kinetic energy, potential energy, and total energy. All the things are same. But small changes will be there. What is the small changes? We have to change the orbits. And we have to consider the angular momentum. There he didn't consider the angular momentum. Now we have to consider the angular momentum. Right? So what is the first equation? Balancing forces. We know. So what are the balancing forces here? According to the first postulate. So electron will revolve around the nucleus in the circular orbits, and electron will revolve around the circular orbits, and balancing forces will be there. Who will provide the necessary centripetal force? Attraction. Yes or no? Coulomb's force of attraction will gives you the necessary centripetal force. So what I can write? So centripetal force is provided by the electrostatic force. Centripetal force is provided by the electrostatic force. Centripetal force formula, so radius from the nucleus r. So I can write it as mv square divided by r, which is equals to, now what I can write? I can write electrostatic force. So tell me what is that? It is K Q1 Q2 by R square. What is Q1? It is ZE into E divided by R square. Right? So one R will be cancelled. So I can write mv square, which is equals to KZE square divided by R. So first equation. The same as like Bohr's model. Why? Because the condition is same. It is correct. So he too took the same equation. Right. So next, second one, according to the Bohr's second postulate. What is that? Angular momentum, which is equals to nh upon 2 pi. Right? Angular momentum, which is equals to what? Nh upon 2 pi. We discussed about this in the last video. Right? You can see that if you have any doubts. Right. So angular momentum I can write as mvr, which is equals to nh by 2 pi. Right? So this is equation 2. So based on these two equations, we can derive whatever we want. We can derive the radius of the orbits. We can derive that particular orbit. What is the speed? Try to write the points. Questions I am raising. So what is the first question? We can calculate the radius of the orbit. You can calculate the velocity of the electron in that particular orbit. If orbit changes, radius changes, velocity also changes. Getting the point? Radius changes, velocity changes, frequency changes. Everything will change. So all the things we have to calculate at each and every orbit. So we are going in depth, try to understand the point. Whatever the orbit it might be, everything we have to calculate. Whether it is radius, whether it is a speed, or whether it is a frequency, whether it is time period, everything we have to calculate now. Based on the two equations. Not that much difficult. Right? So first equation we got and second one we got. Now I am trying to calculate the first part here, which is the radii. Radii of the orbit. Radii in the sense plural, right? So radii of what? Radii of the orbits. So radii of the orbits or the radius of the orbits. Okay. So how to calculate the radii first? So I am trying to calculate what? Radii. So we want, try to see here. So all these two equations. That's it. Whatever if you want to calculate, don't need to buy anything. Whether it is all the things, whatever. So don't need to buy. See, two equations are there. Here R is there. So V we have to eliminate. How we can eliminate V? So for that what I am doing? So first equation I am taking as it is, and second equation we have to eliminate V such that I am doing squaring on both sides for the second equation. So squaring on both sides for equation 2. So what we'll get? We'll get m square v square r square is equals to n square h square divided by 4 pi square. So can I take it as equation 3? Now divide 1 and 3. Divide 1 and 3. Simple, right? So I squared on both sides on this second equation. Now I am dividing 1 and 3. So divide 1 and 3 such that we can eliminate v square. Right? So divide 1 and 3. So divide. So mv square, this side LHS divided by m square v square r square, which is equals to, at the other side mv square, so it is kze square divided by r, and in the denominator this one it is reversed, so it will be 4 pi square divided by m square h square. Right? Clear about the point? Okay. So now cancellations, any cancellations, one r will be cancelled, and v square will be cancelled, and one m will be cancelled. Right? So what we want finally? We want r. So rearrange the things and calculate r. So rearrange the things. So here what are there? So 1 divided by m into r. One m is there and one r is there, which is equals to the other side kz e square 4 pi square divided by m square and h square. Right? This m also can be sent that side such that we can reverse the things, so we can calculate r. So direct. So R which is equals to. So I have sent m that side and we have to reverse the thing. So it will be m square. So n square h square divided by 4 pi square, and m also on that side, and k is there, and z is there, and e square will be there. Right? So this is the radius. So calculation part, do slowly. Why? Because these final equations are important. If you make mistakes here, then whatever the constant values will get, those will be wrong. Okay? So this is the radius. Radius of what? So here we have n. In the sense, this I can write as the radius of the nth orbit. Why? Because here n is there. It is not 1, it is not 2. So I can get this r as the radius of the nth orbit. Clear about the things? What we did? We equated the forces, balancing forces, and we got the first equation. Next, according to the second postulate, we know this, and this is the second equation. By solving equation 1 and 2, we got the radius. Simple. So what is the final thing? Try to write a point, that is the radius of the nth orbit. Radius of the nth orbit. Write a point. Radius of the nth orbit. Radius of the nth orbit. So I can write r as rn, radius of nth orbit. So little I am changing rn, radius of nth orbit, which is equals to, I can write it as n square h square divided by 4 pi square m k z e square. Okay, right? So this is for radius of what? Of the nth orbit. If you want for the first orbit, n value is 1. Second orbit, n value will be 2. Third orbit, n value will be 3. So that is the way you can calculate the radius of the orbit. Now we have to discuss what? Hydrogen atom, right? So now the radius of hydrogen atom. Radius of hydrogen atom. I can write Z equals to 1, right? For hydrogen, atomic number is 1. So Z value will be 1. So I can write Rn, which is equals to n square h square divided by 4 pi square and mass of the electron and k e square. So Z value will be equals to 1. So this is the radius of what? Radius of the hydrogen atom, where Z value which is equals to 1. Okay, try to understand the points. Still more things are there. So what he did, everything he did in the sense, Bohr did, we are trying to learn in this class. So he did some equations, balancing forces, and finally he calculated the radii. So finally he got this. Now, Rn which is equal to n square h square by 4 pi square m k e square. So what he did is, he thought to calculate the radius of the first orbit. Assume this is first orbit, n equals to 1. Okay, n equals to 1. This is nucleus and this is the first orbit. Now he thought to calculate this R1 for hydrogen. Whatever it may be, we can calculate, but assume it is hydrogen atom. So now for the first orbit, how to calculate? Think how to calculate for the first orbit. What is n value? N value will be 1. For the first orbit, n value will be equals to 1. So I can write R1, n is 1. So it will be 1 square h square divided by again 4 pi square m k e square. So n value is 1, h square divided by 4 pi square m e square. And we can substitute the values. 1 square is 1, so it is 6.6 into 10 to the power minus 34 whole square divided by 4 into I square across 10 and 9.1 into 10 to the power minus 31, and the k value is 9 into 10 to the power 9 and into 1.6 into 10 to the power minus 19 whole square. So calculate all these things, so we will get approx like 0.53 into 10 to the power minus 10 in meters. So calculate everything. You will get the radius of the first orbit. Radius of the first orbit is nothing but 0. Very standard thing. You can remember this 0.529 exactly. We rounded off the things and I have done 0.53, right? Into 10 to the power minus 10 in meters. Or we can write it as 0.53 in angstroms, right? 0.53 in angstroms, or you can write 0.53 into 10 to the power minus 10 in meters. So finally, right? So after writing this, try to write a point. Whatever the atom it might be, we can calculate the radius. Whatever the atom it might be, we can calculate the radius by seeing this. So what I can write? So h square divided by this thing. So z, if it is hydrogen, z value is 1, or else z value will be there, right? So see here, h square, 4 pi square m k e square. So if we calculate all the things, what you will get? You will get 0.53 angstroms. So now, radius of the nth orbit of whatever the atom it might be, we can write it as 0.53 angstroms in angstroms. And what are the things remaining? It is n square divided by z. Very, very, very important formula. If you want to calculate the radius, please try to remember this formula, not that much difficult. So radius will be 0.53 in angstroms and n square divided by z. N square divided by z. Right? Clear about the point? So where n is quantum number or orbit number, principal quantum number or orbit number. So n is principal quantum number or orbit number, and z is atomic number. We know. Okay. So now try to understand the things. So now the radius of the nth orbit or any orbit. So z is constant. It depends on the atom. And 0.53 angstroms also constant, because electron is evolving, all the things are constants here. So 0.53 also constant and z is constant. So I can write Rn is directly proportional to n square. Try to understand this point. The radius of all the orbits is directly proportional to the square of the principal quantum number or the orbit number. Right? So now, for example, if n value, if I give 1, so Rn value is 1. So if n value is 2, Rn value will be 4. Try to understand the point. If n value is 3, third orbit, now Rn value is 9. So the ratio I can write it as R1, R2, R3 and so on, like 1, 2 square, 4 and 9. So by seeing this, what we can conclude? The gap between the orbit numbers, the gap between the orbits is not same. Yes or no? So second orbit we are trying to draw like this. So now for example this is R1, and what about the space between the first orbit and the second orbit? Will be different. And what about the space between the second orbit and the third orbit? Will be different. Trying to understand this concept. So with respect to the orbit number, the radius varies. It won't be fixed. It is different. The ratio is what? 1:4:9 and so on. Theory questions, chances will be there, right? So Rn is directly proportional to n square. So the ratio will be like this, and the radius will vary for any atom will be in the form of square of the principal quantum number. This is about the radius, right? So we can calculate for R2, we can calculate R3 and so on. So what will change? N value will change. So if you want to calculate R2, directly I can tell. So tell me, directly how you can tell? So R1 value is 0.53 angstroms. Now this 0.53, you have to multiply with 4. That's all. If you want to calculate R2, directly I can tell 4 times of R1. 4 times of R1. So 4 into 0.53 angstroms. So if you want to calculate R3, so 9. So I can write as 9 times of 0.53 angstroms. So this is the way we can calculate whatever the radius it might be. So clear about the radius point? So the space or the radius of all the orbits is not fixed. The ratio is different. We didn't get 1:1:1, right? So we got 1:4:9 and so on. right? So the gap will be different. So these are the formulas. This formula is very important for the problems. They'll give some atomic number, they'll give some principal quantum number, find the radius. Or the radius of one atom, they will compare to the another principal quantum number to the another atom. What is the ratio of the radius? Right? Now, next, velocity. The velocity of the electron, velocity in the sense speed, direction already we know, we have to draw the tangent, right? So speed you can write, or velocity in the sense direction we know, we are trying to calculate only the magnitude of velocity. You can keep velocity also, not a problem, speed also not a problem, right? So velocity of the electron. So second point, velocity of the electron in the orbit. Velocity of the electron in the orbit. I am not writing that, try to understand. Velocity of the orbit. So velocity of the electron in the orbit. So how to calculate velocity? How to calculate velocity? All these formulas what we got, please try to write aside. Those will be important. Okay. So how to calculate velocity of the electron? So again the same equations, what are those? mv square, which is equals to what we got? Kz e square divided by r. Equation 1. In the radius I have written equation 1, the same I have written directly. mv square by r, kz e square by r square, r will be cancelled. So first equation. So second equation, angular momentum which is equals to nh by 2 pi. So second equation is the same. Right? Now, try to understand how we can solve velocity now. Right, see. So now from equation 2 directly we can solve. See, I consider equation 2. Consider equation 2. So now we want velocity. So v which is equals to, can I write nh divided by 2 pi, m and r will go to the other side, so it will be 2 pi mr. Simple. Is that okay? So v which is equals to nh divided by 2 pi mr. So this is what? This is the velocity. So now what we can write? So velocity of nth orbit if you want. Generally I have written velocity. So velocity of the nth orbit. So velocity of the nth orbit. So what I can write? So Vn which is equals to, here n is there. So this is velocity of the nth orbit. Why? Because n already we wrote. So it is nh divided by 2 pi mass of the electron in the radius of that nth orbit. So velocity depends on radius. Radius already we calculated. So tell me what is the radius of the nth orbit? 0.529 exactly, or round off 0.53 in angstroms. And what we get? N square divided by z we got in the radius. Right? So we got it as Rn 0.53 angstroms, n square divided by z. So that is the radius of what? Radius of the nth orbit. Now, so substitute here, so we can calculate the velocity of the nth orbit. Simple. So what I can write Vn which is equals to nh divided by 2 pi m. So what is Rn? That will be 0.53 in angstroms and n square divided by z. Right? So one n will be cancelled. So finally Vn I can write it as z will go to the numerator. So constants right one side. So h by 2 pi m, and this is also constant 0.53 in angstroms, and z will go to the numerator. So it will be z by n. This is the velocity. Okay, so h divided by 2 pi m into 0.53 angstroms into z by n. This is the velocity of the nth orbit. See, n is there. So nth orbit. So we can calculate this. That's all. What a big deal. So h we know the value 2 constant, pi constant, m constant, and 0.53 angstroms constant, right? So z by n. So what we can finally conclude, Vn is directly proportional to z divided by n. Right? So if z is also constant, It depends on the question, right? If two atoms, if they are comparing the velocities of the different orbits, then Z by L. If Z is also constant, then I can write the inversely proportional to only atomic number. So consider I am taking only the same atom, so try to discuss that. So atomic number is also same, that is also the constant. So what I can tell now, if orbit number is increasing, then velocity decreases. Try to write that point. If orbit number is increasing, principal quantum number of the orbit number is increasing, then what will happen to the velocity? Velocity decreases. If n increases, m decreases. So what is the shortcut formula to remember for this velocity after calculating all these things? See? So we'll get a formula like this. Is that clear? So first equation not that much important here. In the flow I have written. So second equation is enough. So we have to eliminate this r already we calculated, that I substituted here, and we can say that we got Z by L. Simple topic. Derivation also not that much difficult to by heart. It is easy to remember, right? Now after calculating all these things. See, after calculating all these things, you will get like velocity which is equals to, in comparison with speed of light. Why? Because here 10 to the power minus 10, here 10 to the power minus 31. So all these things if you calculate, you will get V value, velocity of the nth orbit. Velocity of nth orbit, you will get like speed of light divided by 137 into Z by L. Very important formula, right? So very important formula. So radius final equations and velocity final equations, very important. So radius final equations 0.53 angstroms into n square by z. Now your velocity at nth orbit, it is, what is c? C is the speed of light, 3 into 10 to the power 8 meter per second divided by what? 137 into Z by N. C is constant. So, sir, how you got this? Calculate this. Have calculators? Calculate this. 6.6 into 10 to the power minus 34 2 into some nonsense, this, some nonsense, and this one. So, you will get in the ratio of C by 137. Z by N is constant. Right? So speed of light divided by 137. If you do, this value and this value will be same. It is easy to remember. So that's why I have written this. Right? So very important equation in the velocity. So please remember this. N value increases and as the speed value decreases. Clear about the velocities? Right? So now at whatever the orbit is might be, we can calculate the velocity. We can calculate the radius. Clear? Next we will calculate energies. Okay? So next we will calculate energies. Okay, so we'll calculate energy. Energy. Sir, energy in the sense two types of energies will be there. So what are those? We'll calculate everything: kinetic energy, potential energy, and later on total energy. Right? The same way what he calculated. What he calculated in the sense what? Rydberg. So kinetic energy how we can calculate from equation 1. See what is equation 1? So that is nothing but mv square which is equals to kz e square divided by r. Right? mv square by r which is equals to kz e square by r square, r will be cancelled. We know that. So this is equation 1. From equation 1 we can calculate the kinetic energy. So multiply with half on both sides. Multiply with half on both sides. So what I can write? So half mv square which is equals to kz e square divided by 2 times of r, where kinetic energy of the electron is nothing but kz e square divided by 2r. So it depends on radius. So kinetic energy of all the orbits is constant? No, it depends on the radius again. Is that okay? For example, kinetic energy of the first orbit we want. So R1 you have to consider. So kinetic energy of the second orbit R2, kinetic energy of the third orbit R3. So kinetic energy of the nth orbit, kinetic energy of what? Nth orbit. So what I can write it is kz e square divided by 2 times of Rn. Right? So if it is 1 R1, 2 R2, 3 R3 and so on. Right? So next, potential energy. This is kinetic energy. Next we will see potential energy. So the same thing what Rutherford did, the same here also potential energy formula. It is K Q1 Q2 divided by R. Right? So substitute the values K Q1 nucleus, Q2 electron divided by the distance between them. So what I can write? I can write it as minus K Z square divided by R, that is nothing but potential energy represented with U. So this is also depends on what? Depends on the radius. So potential energy of the nth orbit, which is equals to minus K Z square divided by Rn. So kinetic energy in the nth orbit and the potential energy in the nth orbit. What is minus indicates? Already we discussed. What is this minus? Always the electrons is bound to the nucleus or it is free to move. It is bound to the nucleus. So this minus indicates the stability of the electron. Stability of the atom also we can call. Right? So it is bound. The electrons is bounded to what? Bounded to the nucleus. So to attain the stability, you will get that minus. Right. Next, total energy. So calculate total energy. Total energy. Okay. So what is total energy? That is nothing but the sum of kinetic energy and potential energy. So what is kinetic energy? It is kz e square divided by 2r. And what is potential energy? It is minus k z e square divided by r. So n orbit also we can take, but I am writing it as a, don't worry about that. So total energy finally we can get it as the same, I think. So it is minus k z e square divided by z e square, right? Divided by 2r. So total energy I can write as what? I can write as minus k z e square by 2r. See, potential energy and total energy, it is by 2, it is half. And kinetic energy and total energy is same but negative. So total energy also we got in the negative presence to attain the stability. The electrons will bound to the nucleus. We know that. Right? Try to see the relation. That relation is very important. So what is the relation between? Can I write here? Relation between kinetic energy, potential energy, and total energy. Relation between kinetic, potential, and total energy. Right. So what is the relation? See, kinetic energy, magnitude I am taking now. Magnitude I am taking now. Why? Because minus is also there. I am neglecting that minus. I am taking only the magnitude modulus. Okay. So kinetic energy and total energy is same. So what I can write? Modulus of kinetic energy and modulus of total energy. So both are the same. Now what do you mean by potential energy? So here it is kz square by 2r and here it is kz square by r. So now I can write it as modulus of potential energy divided by 2. Can I write? So if I divide with 2 potential energy, then only that will be equal to kinetic energy as well as total energy. So this is the final relation, very important for the problems. So they'll ask the ratio also, ratio of kinetic energy, total energy and potential energy. So tell me the ratio. So next point. So the ratio of kinetic energy, potential energy and total energy. So what I can write? If I write it as 1:1, then total energy I have written here, potential energy I have written here. So don't be confused. Right? So kinetic energy, total energy and potential energy. So what I can write? Kinetic energy 1. If total energy is also 1, if kinetic energy is 1, total energy is also 1, then what about potential energy? That will be 1/2. So I can write as 1:1:1 1 by 2. So we can write it as 2:1. Visible? Right? So it will be 2:1. So kinetic energy, total energy, potential energy. Ratio will be 2:1. So why? Because this relation, by seeing the equations, we can tell them. Right? Now try to understand the thing. So whatever the orbit it might be, we can calculate the kinetic energy, we can calculate the potential energy, and we can calculate the total energy and the relation between them. Right? Very important for the problems. Right? So Bohr, what he did up to now? Try to go back to 19th century. So what he tried to do? He tried to calculate the radius, velocity, and energy, and later on many more things are there. Right? So he tried to calculate what J.J. Thomson disadvantage. He tried to took up now. Try to understand the point. Very important story. What is the J.J. Thomson disadvantage? Try to think. J.J. Thomson disadvantage. So I think I said like this. Okay. So he considered a chamber. In that he sent a gas. Right. So he inside it is a gas is there inside. Sorry. So gas is there inside, and he sent a light of wavelength lambda. So he placed the zinc sulfide screen. So what he can see on the zinc sulfide screen, whatever the light he sent, he has seen that? No. So some part of the light is missed. Where that went? That took by the gas, and they went to the higher excited state. Whatever the energy which is taken by the gas, that is missed on the screen. Now later on, after some time, what happened? The gas releases that energy, and after some time, whatever the gas, whatever the lines which is missed, and that it is appeared. So he didn't try to explain about that. So now Bohr is trying to explain about that. He gave the names as emission spectrums and absorption spectrum. Already we know about that. What is that? Emission spectrum and absorption spectrum. Those spectrums are nothing but the radiations emitted by the gas. Try to write all the points. So why those lines missed first? In the sense, the energy what it is coming, so the gas took that energy and went into the higher energy levels. So that is missed. So later on, whatever the atoms or whatever the electrons, how much time it will be in the higher excited states? Very small time. In the order of 10 to the power minus 8. In the order of 10 to the power minus 8. Very small time. So if stability is there, okay. If stability won't be there at the higher energy levels, so what will happen? Again, they will come back. While coming down, what will happen? The energy will be released. See, it is in the higher energy level coming back. So while coming back, the energy will be released. That energy will be seen on the screen according to the Thomson. Now, what is that energy? What is the wavelength of that energy? How to calculate that? All the things are set by the Bohr. Set by the Bohr, right? So now we will see all the things. So what is the frequency of that emitted thing, and what is the wavelength of that? Everything we will try to calculate. Keep the heading: wavelength of emitted radiation. Next point under the Bohr's theory of hydrogen atom. Wavelength of the emitted radiation. Wavelength of emitted radiation. Start. Try to calculate. So, next, wavelength of emitted radiation. Wavelength of emitted radiation, right? So, how to calculate this? What do you mean by that emitted radiation? Clear about the point? Now, we will see according to the diagram. See, so this is nucleus, and this is first orbit, and this is second orbit, right? So, first orbit, and this is second orbit. Already we have seen the last class, just a quick revision, okay? So, consider an electron. Consider an electron which is there in the second orbit. Okay, so consider an electron which is there in the second orbit. Okay, so consider an electron which is there in the second orbit, higher excited level. So now it is trying to come back to its ground state. N equals to 1, we call it as ground state. So from the higher energy level, it is trying to come back to its original level of the ground state. So while coming down, definitely it will release some energy. It will release some energy, right? So we will try to calculate this energy first. Already we have seen the formula. So tell me, what is the formula? How much energy it will release? How much energy it will release? That depends on the energy of the second orbit and the energy of the first orbit. Energy of the second orbit and the energy of the first orbit. So what I can write now? I can write E2 minus E1. E2 minus E1, which is equals to HF. What is this E? Total energy or the kinetic energy or potential energy of this object orbit. That is the total energy of that orbit and the total energy of the first orbit. The difference between these two, which is equal to HF. Already total energy we know. So tell me, what is the total energy formula? Total energy. Just now we have seen. Total energy is nothing but equals to kinetic energy. So minus. So minus. We will try to discuss about total energy little more, right? So total energy, which is equals to minus times of kinetic energy. What is kinetic energy? It is kz square divided by 2r. Try to understand the things. So little about the total energy we will discuss. Okay. So total energy, which is equals to minus kz square divided by 2r. Now we know about r. Try to substitute here nth orbit. So En, which is equals to minus kz square divided by 2 times of Rn. What is Rn? That is 0.53 in angstroms and n square divided by z. Very important, very important. So if you want, you can continue there the total energy, or else write in the note. Okay. So energy at nth orbit is minus kz square by 2 times of 0.53 angstroms and n square divided by z. So energy at nth orbit, which is equals to z, will go to the numerator and n square. So it will be minus k times of z. So I am not writing z there. Z will take out. So constant we will see here. So it is k e square divided by 2 times of 0.53 in angstroms, right? So z will go to the numerator, z square by n square in electron volts. Why? Because wavelength in angstroms, so energy will be in electron volts. I said in the dual nature, right? So wavelength. So this distance is in angstrom. So if you convert all the things, so smaller unit of energy we have to take, that is electron volt. So what is the total energy? This is the total energy at the nth orbit. So if you calculate all these things, so calculate 9 into 10 to the power minus 1.6 into 10 to the power minus 19 whole square divided by 2 times of all these things, you will get a constant, very important, which is minus 13.6 z square divided by n square in electron volts. If I convert it to electron volts again, so in joules you will get finally. And after that, if you convert into electron volts, finally you will get minus 13.6. Try to remember, very important value. You can calculate this and try to convert. So initially, if you write 9 into 10 to the power 9, that is not in CGS, right? That is in the normal things. And 1.6 into 10 to the power minus 19. And after that, you have to convert into electron volts. So generally, you get in joules. So that joules you have to convert into electron volts in the sense, what you have to do? Again, you have to divide with 1.6 into 10 to the power minus 19 again. So after dividing that, this joules will be converted to electron volts, so we know that. Right? So energy at the nth orbit, total energy. I'm not talking about total kinetic energy, I'm not talking about the potential energy, that we will see later. And why big paper column, there everything I try to write. Okay? So here, energy at the nth orbit, what is the formula? Minus, very important formula. Minus 13.6 z square by n square in electron volts. So this is energy at what? Energy at the nth orbit. Right? So now V2 minus E1, which is equals to HF. Go back to the concept after knowing about this total energy. Go back to the concept. So second to the first, an electron is coming. So energy will be released by the electron. Energy will be released or energy will be gained. Energy will be released. Well, if energy gains, then what will happen from n equals to 2, it will go to n equals to 3. Why it will come back? Right? So energy will be released. So that energy we call it as emission radiation. Radiation, emission or emission radiation. Right? So emission radiation or emitted radiation or emission radiation, right? So E2 minus E1 which is equals to what? HF. Now start calculating. So what I can write down from this? What is E2? Come back to here. E2 minus 13.6 z square by 2 square, right? So minus 13.6 z square divided by 2, in the sense here 2 will be there, so it will be 2 square minus of minus the formula. So again y minus, that is there in the formula here. So minus 13.6, we know that z square divided by now 1. So n value will be the first orbit. So 1 square, which is equals to h. Right? Clear about the point? So finally I can write it as minus 13.6 z square by 4 minus of minus plus 13.6 z square by 1, which is equals to h. So like this we can calculate whatever the orbit it may be, not only E2 and E1, whatever the orbit N1 and 2. So we can calculate like this. So take 13.6 z square common. So what you get? 1 minus 1 by 4, which is equals to h. So this is the amount of the energy that is produced. So if they ask to calculate frequency, we can calculate. So this h will go to the other side, right? So this is frequency. So if you ask to calculate frequency, this will be the frequency. So 13.6 z square divided by h into how much? 4 minus 1, it will be 3 by 4, which is equals to frequency. So if I consider it as an example of 2 to 1, for example, N2 to N1, you can write the formulas. So we'll write a generalized formula and we'll be. Okay? So clear about the total energy. Now, instead of considering 2 to 1, so we will consider N1 to N2 now. That N1 and N2, it depends. We'll see later in the series. Okay? So assume the energy from N2 to energy at N1, which is equals to h. So what I can write N2? So directly can I write? So it will be minus 13.6 z square divided by N2 square minus of minus plus 13.6 z square divided by N1 square, which is equals to h. So if I take 13.6 and z square common, it will be 1 by n1 square minus 1 by n2 square, which is equals to h. Very important formula. Very important formula. Right? So if they ask to calculate energy, so this is the energy. Right? So how much energy? So this is nothing but, so this is E2 minus E1, how much energy radiated or emitted out. This is the energy emitted out. This is the energy which is emitted out. So therefore, energy radiated. Energy radiated, I can write it as 13.6 z square into 1 by n1 square minus 1 by n2 square. Energy radiated. The h won't come. Frequency of the emitted radiation. If they ask frequency of the emitted radiation, frequency of emitted radiation. Frequency of emitted radiation. So h will go that side. That's it. So which is equals to 13.6 z square 1 by n1 square minus 1 by n2 square divided by what? Divided by h. So this is frequency of the emitted radiation. For example, if they ask to calculate the wavelength of the emitted radiation, everything is related. Already we discussed. So can I have this? This is just an example. These are the equations that we have to remember. So what is the relation between energy and wavelength? We discussed in dual nature, right? So what is the energy emitted, which is equals to hf, and I can write as hc by lambda. The equation is energy which is equals to h mu or hf. So I can write it as equals to hc by lambda. What is the energy now which is emitted is this one. So if they ask to calculate the wavelength, so I can write it as 13.6 z square into 1 by n1 square minus 1 by n2 square, which is equals to hc by lambda. Just energy I have write, not frequency. Just energy I have written, which is equals to hc by lambda. Now what we want? Wavelength. So before that we will calculate 1 by lambda. 1 by lambda we call it as a wave number. We call it as wave number. Right? What do you mean by that? Wave number. Number of waves emitted per meter. Per meter. We call it as wave number. What is wave number? Number of waves emitted per meter. We call it as wave number. Try to write down. Number of waves emitted per meter. We call it as wave number. What is frequency? Number of waves emitted per second. Don't be confused. What is frequency? Number of waves emitted per second. We call it as frequency. What is wave number? Number of waves emitted per meter. We call it as wave number. So 1 by lambda, we call it as wave number. So symbol will be V bar. V bar. We call it as what? Wave number. So which is equals to 1 by lambda. Hc will go this side. So it will be 13.6. Z square divided by Hc into 1 by n1 square minus 1 by n2 square. Right? Clear about the point? So wave number is nothing but 1 by lambda, that is 13.6 Z square by Hc into 1 by n1 square minus 1 by n2 square. Here one more scientist entered. Try to understand the story. One more scientist, he entered and he is doing the relevant experiments and he got some value. Based on this radius, velocity and all, he is doing some experiments and he got some value. And the scientist's name is Rydberg. What is that? Rydberg. Rydberg is the scientist. So what he did actually, he is doing some experiments on the same stories but not in the same manner. He is doing the same experiments on this atoms, nuclei and all this nonsense about the electrons which is revolving. Right? So finally he got the relation for wave number. He got the relation for wave number which is exactly equal to this. Which is exactly equal to that. That experiment they didn't give in the NCERT. So what he did, we don't want that. So finally what he got, that is important. Right? So what he got this Rydberg after doing this, the same equation which is 1 by lambda which is equals to 13.6 Z square by Hc into 1 by n1 square minus 1 by n2 square. The same thing he got. So he did the same thing. No. So this constant, whatever it is there here, he gave his name. Constant, right? 13.6 in electron volts and Hc, H is constant, C is constant. He calculated all the things and he got a value. So 13.6 in electron volts divided by Hc, he got a value after calculating this, that is 1.097 into 10 to the power 7 per meter. Why per meter? 1 by lambda. Z is constant and this is also constant. So this will having some unit. Okay, so that is per meter. So after calculating this, he got a value called 1.097 into 10 to the power 7 per meter and he kept his name. Why? Because he did the same. Bohr also accepted, okay, chalo bhai, take your name. So he said that R value will be 1.097 into 10 to the power 7 per meter. So that constant we call as Rydberg constant. What constant? Rydberg constant. Is good? So Rydberg constant. What is the constant? So it is 1.097 into 10 to the power 7. So therefore, finally, right? Understanding the point? We'll revise the thing. Okay. So therefore, finally, we got the wave number relation as 1 by lambda. Okay. So I can write it as 1 by lambda, which is equals to, I can write it as what? R Z square, right? So this complete thing I have written as R Z square into 1 by n1 square minus 1 by n2 square. Right? So wavelength from this we can calculate. If you know 1 by lambda, you can calculate wave number or not. Inverse to that. So we can calculate wavelength. If you know wavelength, you can calculate energy also. Everything is related here. Don't be confused. Okay, so we'll revise the things. More equations we have written. So first we have written about the radius. Clear? Just solve it. Next velocity, next energies, kinetic energy, total energy and potential energy. Now coming back to the emitted radiations. Whenever the electron is coming back from higher excited states to the lower excited states, definitely energy will be released. How much energy will be released? That depends on the orbit numbers. So 2 to 1. So I have written that example. So now I am considering it as N2 to N1. Now the electron is coming from N2 to N1. Whatever it might be that N2, whatever it might be that N1. So what is the final equation? So that is energy is 13.6 n square into 1 by N1 square minus 1 by N2 square. From this equation we can write. Now what is the emitted energy? This much. Emitted frequency gas, that is this much. Right? So with this, what I am trying to calculate, I am trying to calculate the wavelength. So energy, frequency, wavelength. We are interrelated. We have to calculate. If we calculate energy, remaining two terms also we have to calculate in the order. Right? So that's why we are trying to calculate what? Wavelength. So on the way to calculate wavelength, we got another concept. So that's why I have discussed about this wavelength. So by seeing this 1 by lambda, you have to remember it as a wave number. What is wave number? Number of waves emitted per meter. We call it as wave number. What is frequency? The number of waves emitted per second. We call it as frequency. So now we calculate in between. By seeing this, you have to come to an idea that so one more scientist have entered here, and his name is Rydberg, and he is also doing the same experiments on the same thing. And finally, he gave this constant his name, that is called Rydberg constant. That is not a new thing which is introduced. That is there in the formula. That is there in the formula, so instead of writing all these things, directly we can write it as R. So finally we can write it as 1 by lambda equals to R z square into 1 by N1 square minus 1 by N2 square. So this is about wavelength. Right? Wavelength of the emitted radiation. Calculated? Done? So frequency, right? Done? Next. So with this equation part of the concept done. Next, we have to know about the spectral lines. We have to know about the spectral lines of the hydrogen atom. Spectral lines of hydrogen atom. So before going to that, because time is less, only 2-3 minutes time is there. So spectral lines we will see tomorrow. Take a question. Okay. Write a question. So lines I'll write now. The discussion of we'll see tomorrow. Okay, don't worry about it. Okay. So this is ground state. N equals to 1. What is the energy at the ground state? I want all the energies. So if time is there, I do, or else do it. Okay. So what I want, I will tell now. So what I want is, so I draw the lines. About these lines we will see tomorrow. These lines we call as spectral lines. These lines we will call as spectral lines. What do you mean by spectral lines? At that position, how much energy that electron is having, that will be given by this line. So if an electron is there at this line, how much energy will be there? We can calculate. Right? So what is the formula? Minus 13.6 z square by n square. Minus 13.6 z square by n square. So if the electron is there at n equals to 1, what is the energy? We know total energy. Right? So next, n equals to 2. Next, the separation also will be decreased while going to the higher energy levels. Why? Energy decreases. Right? So energy decreases. So say distance is this much, now it will be reduced. Next, still reduced. Still it will be reduced. Still. And after a certain extent, it will be like this. So electron lines only won't be there, they will be matched. So that we call as infinity, that will see tomorrow, right? So now what I want now, try to take a question. Okay. So draw the temporal column, these are the lines and these are the orbit numbers. So this is the first ground state, and first excited state, second excited state, third excited state, and so on up to infinity. This line you can write it as infinity. Right? So now first point what I want is all the lines, I want the kinetic energy of the electron, and I want the potential energy of the electron, and I want the total energy of the electron at each and every orbit. Understood the point? At n equals to 1, what is the kinetic energy? What is the potential energy? What is total energy? At n equals to 2, what is kinetic energy? What is potential energy? What is total energy? Likewise, for all the orbits, up to the possible level, up to 5 at least, up to n equals to 5, I want the kinetic, potential energy and total. Right? So, try to do this. We'll continue in the next class about the spectral lines and disadvantages of the Bohr and de Broglie's hypothesis here, and we'll close the topic. Right? Thank you.